So hello friends. So in a couple of lectures we could complete lock based protocol of concurrency control. So today's we will discuss with deadlock handling. So we'll see how deadlock handling would be taking place while concurrency control top. So a system is deadlocked if there is a set of transactions such that every transaction in the set is waiting for another transaction in the set. So let's assume this particular schedule which has two transactions T1, T2, and deadlock occurs if T1 is waiting for a data which is already occupied by T2, and at the same time T2 is waiting for a data which is already occupied by T1. So here look at the scenario where initially T1 has been granted exclusive lock, that is defined by lock X on X means T1 probably requested for exclusive lock on X from the and lock manager granted the same, and now it tries to update the value of X. But what's happening in granting lock? So it is assumed that if any particular transaction is assigned is granted locks after updation or reading, they should unlock it. But here, unfortunately, T1 hasn't unlocked the data item. Means still any updation on X would still lies in T1 only. Now check the scenario for T2. So T2 has requested exclusive lock on Y, which has also granted to it, and now it will try to write some data, or it will try to update the value of y. In addition, it has also tried to update the value of x. But as I mentioned here, the lock on x hasn't released by T1. So that's why it will wait for lock x on x. Now T2 is trying to update the value of x, but T1 hasn't released the lock from X. So T2 is waiting to do some changes on X that is currently held by T1. And same thing is for here. Wait for lock X on Y. So here there is a scenario where again Y data there was initially lock, exclusive lock, but it has not released by T2. So in both the case T1 is waiting for T2 and T2 is waiting for T1. This is called deadlock. So how to measure deadlock, how to prevent deadlock, or how to detect deadlock, this we will cover in this lecture. So first there are some deadlock prevention strategy. So how to prevent that a particular schedule will fall in a deadlock. So for this we'll have wait dice scheme and wound wait scheme. So wait dice scheme is actually non-preemptive, means if any particular transaction is going to update any particular value, and if a new transaction is demanding the same data which is currently held by this transaction, so either new transaction has to wait, that is non-preemption. But in case of wound wait scheme, it's a preemptive scheme, says that if the older transaction demands the same data which is currently held by a transaction, so it will immediately task will be preemptive, and the old transaction wounds forces rollback of younger transaction. We'll see one by one by using suitable example. So first condition is wait dice scheme, which is a non-preemptive technique. So we'll see how it will be applied, how it will be applicable. When transaction Ti requests a data item currently held by Tj, then Ti is allowed to wait only if it has a timestamp smaller than that of Tj. So very first we need to assign some timestamp for all the transactions. So any particular random value can be assigned to timestamp, but keeping in mind that if we have certain transactions in a schedule, then based on their occurrence, timestamp must be followed. Let's suppose a schedule will have three transactions. Let's assume name that T14, T15, T16. Then if we assign T14 as timestamp 5, then T15 as well as T16 must be assigned value greater than to 5. Not necessarily that we should follow a pattern or something, but keeping in mind that both the younger transaction, that is T15 and T16, must be assigned value which should be greater than to 5. That is the condition we keep in mind. So now we'll again go back to the condition where when transaction Ti requests a data item currently held by Tj. So let's suppose T15 is currently held a data item. So there will be two scenarios. Either T14 is going to make a request for the same data which is currently held by T15, or T16 may have a request for the same data which is currently held by T15. We'll see one by one. So if T14 requests a data item held by T15, then since T14 have come earlier in the schedule in the system, so based on comparison of timestamp value, it can be easily assessed that T14 is the older transaction which has come earlier. So in this case, since it's a non-preemptive, so first T15 would complete its assignment, and then T14 would be assigned to the same data with a suitable lock. So in this case, T14 will wait because T14 is older one. But what happen if T16 would have requested the same data currently held by T15? In this case, T16 will be rolled back, or we can say die. So any new request coming from T16 is not entertained because T16 is younger one, and this is decided based on the comparison of timestamp. So here you can easily check that greater timestamp means the transaction would come younger, and in that case younger transaction will not allow to wait, rather it will be rolled back, means it would be in a die condition. So it is possible that a transaction may die several times before acquiring needed data item, because maybe all the time younger transaction would be assigned a would be requesting to a older one. In that case, it has to roll back. Next is wound wait. It's a preemptive technique. Preemption means if any interruption comes there, immediately move to the control to the newly situation. Its counterpart to wait die scheme. So it says that when transaction Ti requests a data item currently held by Tj, now conditions say that Ti is allowed to wait only if it has timestamp larger than that of Tj. That is, Ti is younger than Tj. So a particular transaction would be younger only if it has larger timestamp. Here there is example T14, T15, T16. So T16 has larger timestamp, means T16 is the younger transaction as compared to T15 or T14. So again we'll take this example and see. Suppose T15 is currently held the data. So again there will be two scenario. Either T14 would make a request for any updation on the same data, or T16 would have requested of the same data which is currently held by T15. So we'll see one by one what happened. As per wound wait scheme, if T16 requests a data item held by T15, then T16 will wait because younger transaction can wait. But if T14 requests a data item that is currently held by T15, then since it's a preemptive technique, so T15 is immediately rolled back. All the control would be pushed over to T14 because older transaction wounds forces rollback of younger transaction. So T14 would be immediately granted all the locks and T15 would be wounded, would be rolled back. So this is difference between wait die and wound wait scheme. Here also maybe if we roll back then wait die scheme. Now what happen in both the scheme, a particular transaction has to roll back. Means he has to start with the new entry. But what happen if any transaction is rolled back? So instead of assigning new value, we'll keep original timestamp. Means the point where any particular transaction have come in the system, the timestamp will remain same. So that next time, otherwise what happen? A starvation condition may be possible if we assign a new transaction number, new timestamp to any rolled back transaction. Third, and this can be controlled by a scheme which is a timeout based scheme. So what we can do, a transaction wait for a lock only for a specified amount of time. So we assign a particular timeout based time for each and every transaction. Up to a particular time it will wait, as and when the time out, wait times out and the transaction is rolled back. So it can also be possible, and in this case deadlocks will not be possible. But it is very difficult to determine good value of timeout interval. So it is very difficult to mention that what may be the good time interval for a particular transaction, so that all transaction would be executed and there should not be any deadlock. So second, in deadlock handling, second is deadlock detection. So how deadlock can be detected? We can construct a wait for graph. So in a graph there are some vertices and some edges. So here vertices means all the transaction in the system. So this particular scenario has four transactions: T25, T26, T27, T28. So they all are assumed as vertices, and edges will be arrow from any transaction to any transaction. So Ti to Tj. And what the meaning of this arrow? It says that, implying that Ti is waiting for Tj to release a data item. So assume that if we take this example, it says that T26 is already held a data item, let's suppose A, and the same data is requested by the transaction T25 for some suitable updation. So this arrow makes that T25 transaction is waiting for a data item that is currently held by T26, and the same will be all for this. So after checking all the transactions instructions of a particular schedule, we can make a wait for graph. And if any request is pending there, so then A is of Ti to Tj is inserted in the wait for graph. And this A's can be removed only when Tj is no longer holding a data item needed by Ti. Means if T25 is making request for a data item that is currently held by T26, and simultaneously T26 released that particular data item, in that case this arrow, this edge would no longer exist. So it will be deleted from the wait for graph. So now since it's a graph, so there is a possibility of cycle also. So deadlock detection would be done based on whether a graph has cycle or not. So the system is in deadlock state if and only if the wait for graph has a cycle, and cycle can be easily detected by the available graph method for the cycle detection. So if any particular cycle detection is there, means there is a deadlock. So check for this, wait for graph without a cycle. So T25 is waiting for T27, T27 is waiting for T26, and T26 is waiting for T27. So there will be no cycle. But if you clearly look this graph here, T27 is waiting some data item that is held by T26. T26 is waiting the data item held by T28, and T28 is waiting data item that is T27 is held. So it's a cycle, and the cycle makes the deadlock detection. So it's a deadlock, and how to break this deadlock? Out of these three transactions, one has to roll back. So all the instructions of any one transaction has to roll back, and then deadlock can be avoided. Deadlock can be eliminated. So after deadlock, how to process the recovery process? So some transaction will have to roll back. So we can assume that there we need to make a victim, and this victim should be chosen to break the deadlock. So we select a transaction as victim that will incur minimum cost. So anytime we should choose transaction which has the minimum cost, and rollback, either it may be partial rollback or it may be total rollback about the transaction and then restart. Complete transaction can be restarted. Again, starvation maybe happens if same transaction is always chosen as a victim based on the cost factor of the transaction. So we should also calculate a method or a suitable process that no a single transaction should be chosen as a victim. Include the number of rollbacks in the cost factor to avoid starvation. So this is about deadlock. So we'll quickly review it. Deadlock, then there is how to handle the deadlock. So either we can have deadlock prevention or deadlock detection. Prevention can be done by certain techniques like wait, die, wound wait, or uh, timeout based uh, timeout based approach. And then deadlock detection can be done by making a wait for graph. And in this graph, if you find any cycle, then we can say that there is a deadlock. And this deadlock can be recovered or can be removed by simply any one transaction should be rolled back so that deadlock can be dropped. So this is all about deadlock handling. I hope you could having better understanding of concurrency control. Thank you for listening me. Thank you.